Okay, okay. Let's solve this problem. Let's solve this problem. Yeah, always solving a problem. That's how we study engineering, right? We are like problem solvers. What? Exceptional question. I can do that, but you won't be happy about that. Okay, so we have a new building to be located in a cold climate. It's being designed with a basement. So we have a basement that has a 200 millimeter thick wall. So this is the wall of the basement. And the inner and outer wall temperatures are 20 and 0 degrees Celsius. So this is the inner wall temperature, Ti is 20 degrees Celsius. And outside, To is going to be 0 degrees Celsius. The architect can specify the wall material to be either aerated concrete block, which is going to be expensive one. So we can make this wall with an expensive aerated concrete block whose thermal conductivity K is 0.15 watt per meter Kelvin, or stone mix concrete, which is cheap. However, it has higher thermal conductivity, so we cannot keep inside warm. So to reduce the conduction heat flux through the stone mix wall, we are going to add an insulation. So this is the original design, and it's going to be pretty expensive. So what we are going to make this wall cheaper with a stone mix concrete. But this time, if we use a stone mix concrete, its thermal conductivity is going to be higher than this aerated concrete block. And what is the thermal conductivity of stone mix concrete? So there's a stone mix concrete, and its thermal conductivity is 1.4. So the thermal conductivity of this stone mix concrete is going to be 1.4 watt per meter Kelvin. What does it mean? You know, the one has this low thermal conductivity, the other one has this high thermal conductivity. That means the rate of heat transfer through this wall is going to be 10 times, almost 10 times less than this one. So if you want to save energy, trying to minimize heat loss through the wall, then you need to use this aerated concrete block. However, of course, this one is going to be more expensive than this one. So what we are going to do is that we are going to propose add-on insulation whose thermal conductivity, where is insulation thermal conductivity? So the thermal conductivity of this R12 insulation is going to be these values. And we can pick a value at the standard temperature, room temperature, 300 Kelvin. So the thermal conductivity of this insulation is going to be 0.027. So the thermal conductivity of insulation is 0.027 watt per meter Kelvin. And the temperature of this inner surface is going to be the same as 20 degrees Celsius. So what we want is, we want to know how thick this insulation should be to have the same rate of heat transfer. So instead of using this expensive material to build this basement wall, we are going to use this cheap stone mix concrete. However, to minimize the heat loss, we are going to add the insulation. And how thick this insulation should be to have the same heat loss between these two. So that's what we want to determine. The thickness of this wall is going to be, this delta X is going to be 200 meters, 200 millimeters, that is 0.2 meter. So delta X of this wall is going to be 0.2 meters, and delta X of this insulation is unknown. So we want to determine this. So how can we determine the thickness of this insulation? We can calculate the rate of heat transfer through this wall and the rate of heat transfer through this wall and say they are equal. That's how we can determine the thickness of this insulation. So let's calculate the rate of heat transfer. How can we do that? The rate of heat transfer can be determined by this equation. Q is delta T, the temperature difference, over the sum of resistances. Then, for this aerated concrete block, what is delta T? 20 degrees Celsius and 0 degrees Celsius. Then what is the resistance? This is solid wall, so the only heat transfer is going to be by conduction. So how do we determine the resistance by conduction? Just for your information, the resistance by conduction is going to be delta X, the thickness of this solid, divided by thermal conductivity K times the cross-sectional area A. Just for your information, convection resistance, R of convection, is going to be 1 over H, convective heat transfer coefficient, times area. And in this case, there is no convection. There should be convection here inside and outside. However, we don't care because we already know the temperature difference between this inner surface and outer surface. So beyond that, not our interest, right? We only use convection resistance here if you do not know the temperature of this wall surface. Instead, if you know the temperature of the air, then you need to consider convection. However, we already know this outer surface temperature and inner surface temperature. So, the outside of these two temperature points don't need in our heat transfer calculation, okay? So, how many resistances between these 2 points? Just one. Conduction resistance between 20 and 0 degrees Celsius. What is the conduction resistance? This one, delta X over thermal conductivity K times area A. What about here? We have 2 layers and they are both conduction heat transfer. So we have one resistance here, that is delta X over Ka. We have another conduction resistance here, delta X over Ka. So the rate of heat transfer in this original design is going to be Q is delta T over R. What is delta T? 20 and 0. 20 degrees Celsius minus 0 degrees Celsius divided by how many resistances? Just one. Delta X over Ka. In this case, delta X is going to be the thickness of this wall, 0.2 meters. The thermal conductivity is 0.15 watt per meter Kelvin. And we can consider the unit area. So we are going to say area is going to be the unit area, 1 square meter What about the thermal, the rate of heat transfer for this modified design with the insulation? We have delta T between 20 and 0. And how many resistances? 2 of them. One for this insulation, the other for this mixed concrete. So we have delta X over Ka plus delta X over Ka. In this case, the area is going to be the unit area, 1 square meter. The thermal conductivity values are available here, 0.027, 1.4. 0.027, 1.4. What is the thickness of the wall? 0.2 meters. Then we assume that they have the same rate of heat transfer. So we have everything but delta X, which is the thickness of the insulation. So you can determine how thick this insulation could be to have the same rate of heat transfer. And the answer is going to be 0.032 meters, which is, in other words, 32 millimeters. So this is the thickness of the insulation that you need to buy from Home Depot, Menards, not Lowe's, because we don't have Lowe's in town, right? Any question? In reality, is this number greater than this one or less than this one? In reality, this is by theory. This is by theory. This number is correct. But in reality, is this higher than this number or less than this number? Higher? How many of you? So this is a 50%, 50%, right? How many of you think that this actual number should be greater than this one? Less than this one? You're right, less than this one. Why is that? Then why is that? The contact, yes, the contact between these two may not be perfect. So there's a gap that will create additional resistance. It is called contact resistance that will decrease the rate of heat transfer. So you don't need this much thickness to have the same rate of heat transfer. Make sense? Right? This is how we design double pane window. You know what is double pane window? We have a one pane of window, another pane of window. What is between these two? So double pane window means we have a one layer of glass and there's another layer of glass. Then what is between these two glasses? Air. In reality, in our original design, it should be vacuum. So we have one glass and another glass, there should be vacuum. So what happened is that we have a conduction resistance here and conduction resistance here. What is between these two? Conduction through what? Convection between the surface and the fluid. What is the fluid? If it is vacuum, there's nothing. So we need to rely on what? Radiation. Then the next question is going to be, Is this glass as hot as the sun? Not really. Then how much radiation do we expect? Extremely small. That's how you design this thermal. We have a vacuum cell between these two layers. So that will, yeah. So there's a vacuum inside. So it has two layers and there's a vacuum between. That's how they design. Then what's going to happen is that while we're using it, the vacuum still is going to be broken, right? So it's going to be filled with air. Is it bad? Not that bad, because if you have an air, then now you cannot rely on the radiation, but you still have what? Convection between the surface and the air inside, and another convection between the air and the surface here. Then is there a significant the fluid movement? Not much. It's very quiet. So the convection heat transfer is very small. Of course, it is not as good as vacuum radiation, but still, that it can minimize the rate of heat transfer. Okay? Any question about this problem? No? There will be at least one problem in your second exam that will use thermal resistor network. So if I give you this problem, can you solve it in your second exam? Yes. You may not be 100% happy, so I prepared another problem here. So let's practice one more time, just to make sure that you are completely happy with thermal resistor network. So we have a dormitory at a large university built 50 years ago, a very old dormitory, has an exterior wall. So we have a wall. This wall and the thickness of this wall is going to be 30 millimeters. So this is 30 millimeters, 0.03 meter, and whose thermal conductivity is only 0.1. Hey, so this one has a very expensive material. The thermal conductivity is 0.1 watt per meter Kelvin. Now, everybody talking about energy savings, so let's reduce the heat losses in the winter. So how can you do that? We are going to apply another additional layer of insulation to the exterior surface. So we are going to add a layer of insulation. So this much. How thick is it? The same 30 millimeters, 0.03 meter, whose thermal conductivity K is 0.029 watt per meter Kelvin. But if you add the insulation, it doesn't look good. So let's cover this insulation with the glass, whose thermal conductivity is 1.4, and the thickness is only 5 millimeters. So we are going to add a glass. The thickness of the glass is going to be 0.005 meter, and the thermal conductivity K is going to be 1.4 watt per meter Kelvin. Determine the heat flux through the original and retrofitted walls when the exterior and interior and exterior air temperatures are 22 and 0 degrees Celsius. So we do not know the temperature of the surface. We only know the temperature of the air inside, which is 22 degrees Celsius, and the air outside, which is 0 degrees Celsius. Then we need convection heat transfer coefficient for here and here. One is 5, the other one is 30. So convection heat transfer coefficient H indoor is 5 watt per meter square Kelvin, and outside HO is going to be 30 watt per meter square Kelvin. Why this one is greater than this one? Why the convection heat transfer coefficient outside is 30 and while the inside is only 5? Here we have air, here we have helium. No, they are both airs, right? Then why one is greater than the other? Why the convection heat transfer coefficient of the air outside is 30 and why the same thing inside is only 5? Because the air inside is quiet, free convection. The air outside is, so it's going to be windy, so it's going to be forced convection, right? Think about this way. What is the difference between free convection and forced convection? Free convection means that there's no fluid movement by force, by an external force. And forced convection means that, there is a force, the flow. So imagine that you want to drive your car in one of the summer days, and there's no AC is working, and when you want to drive your car, what do you want to do? You want to speed up, right? Why is that? If you increase the velocity of your car, the air temperature drops, right? No, the air temperature is constant. Then why you want to accelerate it? Because you want to convert free convection to forced convection. Because forced convection has higher convection heat transfer coefficient. That's why you want to drive faster, trying to increase this H value when AC is not working. Okay? That is the difference between free convection and forced convection. Okay? So let's calculate the heat flux through this wall and the original wall, which has only one layer of solid whose thickness is 0.03 meter, and that has inner surface temperature 22, inner air temperature 22, outer air temperature 0 degrees Celsius. So we want to determine the rate of heat transfer between this one and this one. By the way, it says heat flux. What is the difference between the rate of heat transfer and heat flux? Heat flux is Q double prime. This Q double prime can be determined by Q divided by area. So each prime means divide by length. So if you have a double prime means divide by length square, that is area. So if you want to determine the heat flux, you can just assume that the area is going to be the unit area, 1 square meter. Then do the calculation. That's going to be heat flux. Okay, so let's solve this problem. How many resistances? we had 1 for the convection, 1 through the wall, 1 through the insulation, and 1 through the glass, and finally convection outside. So there are 1, 2, 3, 4, 5 resistances. The temperature is going to be 22 degrees Celsius, 0 degrees Celsius. Then how can we determine the resistance? Each of them, each resistance. For convection heat, convection resistance, it is going to be 1 over HA. Conduction, delta X over KA. Delta X over KA. Delta X over KA. And convection, 1 over HA. What about here? This original wall, we have only 3 resistances: convection, conduction, and convection. We have 2 temperatures, 22 degrees Celsius, 0 degrees Celsius. So the convection resistance is going to be 1 over HA. Conduction, delta X over KA. Conduction, 1 over HA. Then let's calculate Q. Q is going to be delta T over the sum of R. What is delta T? 22 minus 0. 22 degrees Celsius minus 0 degrees Celsius. Then how many resistances? 1, 2, 3, 4, 5. So first, 1 over H, 5 times A. We are going to assume that it's going to be unit area. Area is going to be 1 square meter. 5 times 1 plus delta X, 0.03 divided by K, 0.1 times 1 plus the thickness of this one, 0.03 divided by 0.029 times 1 plus another conduction resistance, 0.005 divided by the thermal conductivity, 1.4 times 1 plus convection outside, 1 over 30 times 1. Then if you do the calculation, you get the rate of heat transfer. The heat flux is going to be 14 watt. What about the rate of heat transfer without insulation, without glass? Then Q can be determined by temperature difference, 22 degrees Celsius minus 0 degrees Celsius. How many resistances? 3. 1 over H. H is 5 times unit area, 1 plus delta X, the thickness, 0.03 divided by thermal conductivity, 0.1 times 1 plus 1 over H, 30 times 1. Then you get the rate of heat transfer, 41.3 watt. So that's how you determine the rate of heat transfer. By the way, this Q is the rate of heat transfer. What we want to determine is the heat flux. And how do you determine heat flux? Q double prime. Heat flux is the rate of heat transfer divided by area. So what is the unit? Watt per meter square. And what is the area? 1 square meter. So the heat flux Q double prime is going to be 14 watt per meter square. Q double prime for this design is going to be 41.3 watt per meter square. So be careful about the unit of the heat flux and the rate of heat transfer. The rate of heat transfer is watt. The heat flux is watt per square meter. Any question? No? No? My son like to listen to the Baby Shark. So whenever we drive the car, I always use this Android Auto or something that automatically the play the Baby Shark. Sometimes when I the turn off my engine and then go to the an office building or somewhere, and then my phone the disconnect from the on Android Auto and just start the playing this Baby Shark anywhere I go. So any question about this problem or thermal resistance network in Cartesian coordinate system? No? It's pretty simple, right? Not really? Do I need to solve one more problem? I hope not. Hey, then what comes next? What about if we have a steady state heat conduction in cylindrical coordinate system, not Cartesian coordinate system, cylindrical coordinate system? Then the question is, can we still use the same thermal resistance network? That's the question, right? Then the answer is not really. No, we can't. Then let's see why we can't. When we have a Cartesian coordinate system, x, y, z, what is the resistance by conduction? And delta x over Ka. What about convection? 1 over Ha. That is the thermal resistance network in Cartesian coordinate system. What about cylindrical coordinate system? When we want to study cylindrical coordinate system, the first question you may have is, why? Can we just use Cartesian coordinate system? There are many engineering applications. Cylindrical coordinate system is much easier than Cartesian coordinate system. One example is, what about if we have an electric wire? Then what is the heat transfer direction? So if you have electric wire from here to the end of this room, what is the heat transfer direction? This way? So if there's electricity, through the electric wire, so one end is going to be very cold, the other end is going to be very hot. Is that what you expect? Really? No. The heat transfer direction. If this is the heat transfer direction, if I, install, the electric wire between Mount Pleasant and Michigan, Mount Pleasant is in Michigan, Mount Pleasant and, the Midland, one in Midland should be already on fire, because if the heat transfer direction is in the, the axial direction of this, the cylindrical coordinate system, the longer the distance, you will have higher the temperature. Does it make sense? No. Heat transfer direction is not the axial direction. It's going to be radial direction. if the heat transfer is this way. Let's think about another example. So we have a water pipe, hot water pipe. So there's a hot water flowing this way. Then what is the heat transfer direction? In the axial direction? If heat transfers in the axial direction, then when you touch the pipe, you shouldn't feel it is hot. Because heat transfers this way. If the heat doesn't go to your skin, how can you feel that it is hot? When there is a hot water pipe, when you touch it, you feel that it is hot, right? Why is that? Because there is a heat transfer from the pipe to your skin. Then what is the direction of heat transfer? Radial direction. The heat transfer direction is this way, radial direction. The heat transfer direction is going to be the radial direction. So when you have this pipe system or the electric wire systems, heat transfer direction is going to be radial direction. Then let's talk about that. If you want to study heat transfer in radial direction, then what is the coordinate system that we have to use? If you look at the heat transfer in this way, so you're looking at in this way, right? This way. Okay, so the cross-sectional area. So we have this water pipe. And there's hot water inside. Let's say the water temperature is near the boiling temperature, 100 degrees Celsius. Can I say this is near boiling temperature? I can't, because we studied thermodynamics. Whether it is close to the boiling temperature or not depends on the pressure inside the system. So if I say the pressure is near, the 100 kilopascal, and the temperature is 100 degrees Celsius, now you can say that it's close to the boiling temperature. Anyway, what is the temperature outside? 20 degrees Celsius. Then what is the direction of heat transfer? From this hot water inside to the air outside. So the heat transfer direction is this way. From inside to the outside, there's this Q. Then, what kind of heat transfer? Is it conduction, convection, or radiation? It's going to be first convection, conduction, and radiation. So there are three resistances. First is convection, because whatever the fluid is moving, and this is conduction because it's a solid, and convection outside because this is the heat transfer from the outmost surface and the surrounding fluid, which is air. Then, can we use the resistances that we studied from Cartesian coordinate system? Let's see. So there's a convection resistance. So what is the convection resistance? Here is going to be R by convection, which is 1 over HA. The H is going to be convection heat transfer coefficient depending on the material and the fluid velocity. And what about this area? This area is going to be, if we say this is R1 and this is R2, this area is going to be 2 pi R1 times the length of pipe. I'm going to say the length is going to be L. So that's how you can determine convection resistance. What about conduction resistance? This one. Can we use this one? Let's see. R by conduction is going to be delta X over Ka. Then what is this delta X? R2 minus R1. Yeah, we can do that. And K is going to be the material property from this material. What about this area? For this resistance, should we use this inner surface area, like a 2 pi R1 times L, or should we use this outer surface area? Problem is, when we calculate this conduction resistance, the cross-sectional area in the direction of heat transfer is changing. It is increasing, right? Therefore, we cannot use this resistance. So, using this convection resistance is okay, but using this conduction resistance is not, because this area is not constant. So what can we do? For this conduction resistance, we need to come up with another equation. That is this one here. Conduction resistance in a cylindrical coordinate system can be determined by R of conduction in cylindrical coordinate system is going to be natural log R2 over R1 over 2 pi K L. So that is the only difference between cylindrical coordinate system and Cartesian coordinate system. So convection resistance is the same, but conduction resistance is different between Cartesian coordinate system and cylindrical coordinate system. Okay, that's the only difference. Then based on this new resistance, let's come up with the rate of heat transfer equation if you have a pipe with some insulation. So I have a water pipe. We are going to install between this engineering technology building and what is the building over there? Bioscience building. So we are going to install water pipe between here and the bioscience building. And we want to make sure the water inside is not going to be frozen in winter. So how can you avoid this water being frozen in winter? You can add the insulation. This much. By the way, the real, practical answer is bury them underground. That's the best way. Instead of, leaving this, the pipe in the middle of, the air. Right? No? When you drive, on a highway or anywhere, sometimes when you want to, cross a bridge, what does it say on the bridge? Come again? It freezes, right? What exactly it says? I don't remember. Huh? Right. The bridge ices before the road. Why is that? Because the heat transfer from the bridge is much greater than heat transfer from underground. So if you want to install, the water pipe between this building and bioscience building, and the easiest way, the simplest way is that just connect a pipe between here and there. But if it is exposed to the air, then there is a great chance to be frozen, even though you add a lot of insulation. So the best way is that, you need to, bury them underground so you can minimize the heat loss, right? Why is that? Why is that? Why burying underground is, give you less heat transfer than hanging this pipe in the middle of air? Kind of. So when you bury the pipe underground, that means that you are going to rely on what? What kind of heat transfer is that? Conduction, because the fluid is the soil is not moving, right? But if you place them on, in the air, it's going to be conduction. So conduction is much slower than convection, right? If you are not sure, always think about, the one example. When you want to, to take a bath. Today, I was too tired, so I'm going to take a bath. And then you forgot to turn on the hot water. So it was completely, the freezing water in the bath. Can you jump in? No, you don't want, right? You want to turn the hot water on. So if you turn the hot water on, you think that, the temperature of the water evenly goes up? No, only the temperature of the water near the, the hot water going down is going to go up first, right? Then how are we going to, the transfer heat from where the hot water pours down to the, to the other end of the, the bath? We're going to stir. Why is that? Because it's a mass transfer. Mass transfer is way faster than heat transfer, right? I don't know why I said that, but that's good to know, right? So usually when there is a convection and conduction, convection is much easier to transfer heat because you can, the transfer mass rather than just rely on pure heat transfer from one molecule to another molecule. That's why, the most of energy storage materials in terms of heat are made of liquid rather than solid. Because if you have an energy storage material made by liquid, transferring heat is super easy. You can just pour this hot water into that, into that bottle and then move it. That will be much easier than, steel pipe connect, one end and the other end. You're holding here. You don't feel that heat, right? Because the conduction is very slow. That's why, we bury, the water pipe underground because conduction is slower than convection. Anyway, so for this pipe system, we are going to add an insulation, which is this blue. And there's an air outside, which is going to be this green. Then what is the heat transfer from this hot water, which is this red? The direction of heat transfer is going to be from inside to the outside. And how many heat transfers? 1, 2, 3, 4. So conduction, convection, conduction, conduction, and convection. So this one is T, I, T, O, and this resistance is going to be 1 over HA. By the way, this is, the inner radius is R1. This one is R2. This one is R3. Then 1 over HA is going to be 1 over H times 2 pi R1 times the length of the tube. What about this? Conduction resistance is going to be natural log R2 over R1 over 2 pi Kf. What about this? Natural log R3 over R2 over 2 pi Kf. What about this one? 1 over HA. In this case, this area is going to be 1 over H times 2 pi R3 times F. Then if you want to determine the rate of heat transfer, this one, Q is going to be a delta T over R. This delta T is going to be Ti minus To. And how many resistances between two temperature points? 1, 2, 3, 4. So it's going to be 1 over H 2 pi R1 F plus natural log R2 over R1 divided by 2 pi Kf plus natural log R3 over R2 over 2 pi Kf plus 1 over H times 2 pi R3F. So that's how you determine the rate of heat transfer. Any question? So you can see this is the new one in cylindrical coordinate system. Then we have one more coordinate system. Yes. What? Your question? Okay, your question. So the K value should be different between the pipe and the insulation material. You mean the conduction here? That is already taken into account here, natural over R3 over R2. The last one is spherical coordinate system. Of course, as we expect, the conduction resistance is going to be different. And what is the new conduction resistance for spherical coordinate system is going to be this one. 1 over R1 minus 1 over R2 divided by 4 times pi K, but this is just for your reference. We are not going to have this, the resistance in our second exam because spherical coordinate system is much less widely used than cylindrical coordinate system or Cartesian coordinate system. Spherical coordinate system is very rare in heat transfer. Cartesian and cylindrical, they are quite popular. Spherical coordinate system is very rare unless you want to study fireball, no, sun. Usually having this, the spherical shape is very uncommon in engineering. So this is just for your reference, okay? So that's everything about thermal resistor network in cylindrical coordinate system, and we have a new problem that we are going to solve together. How many problems? Just this one. So after this thermal resistor network is going to be over, and we are going to move to steady state heat conduction with heat generation. Okay, so we have a thin electrical heater is wrapped around the outer surface of a long cylindrical tube. So we have this long cylindrical tube. Wrapping around with a electrical heater. And why do we do that? Maybe we want to, prevent from, the freezing whatever inside, to maintain the inner surface of the tube at a temperature of 6 degrees Celsius. So this point, inner surface, is going to be 6 degrees Celsius. And we have the information about the inner radius and outer radius, 24 millimeters and 78 millimeters. We have the thermal conductivity of this tube. And there's a contact resistance between the heater and the outer surface of the tube. So we have a contact resistance that we need to consider. That value is available. Oh, that's a typo. I have two of them. Just this one, okay? The outer surface of the heater is exposed to a fluid with the temperature minus 10 degrees Celsius. And the convection coefficient is 100 watt per meter square Kelvin. Okay, so the temperature outside is going to be minus 10 degrees Celsius. And then we have the temperature of the heater is 25 degrees Celsius. So we have a temperature difference between inner surface and outer fluid. So the heat transfer direction is the radial direction. Then if you want to study radial, the heat transfer in radial direction, what do you want to see? You want to look at, in this way, right? So our heat transfer problem is going to be, we have a tube like this. We have a resistance heater around like this. So this is a heater. And this is pipe. I'm going to say this is a green pipe. So there's a pipe, and we have a heater around it. And the temperature of the inner surface, I'm going to say Ti is going to be what? 6 degrees Celsius. And this is the heater. We have the temperature of the heater. The heater, H, okay. pH is going to be 25 degrees Celsius. We have the fluid outside, T infinite, is going to be minus 10 degrees Celsius. How many resistances? One for the conduction, one for the contact resistance, and one for this convection. So there are 3 resistances. Then this conduction heat transfer, R by conduction, is going to be natural log R2 over R1 over 2 pi KR, which is what we just studied in the previous slide. And we have a convection resistance here, R by convection, which is 1 over HA. By the way, this A is going to be 2 pi R2 times R. And we have this contact resistance, which is 0.01 meter Kelvin per watt. So we have 3 resistances. R1 is going to be the inner radius, 24 millimeters, 0.024 meter. R2 is going to be the outer radius, 0.078 meter. And the thermal conductivity is 10 watt per meter Kelvin. What is the length of the tube? Or do we have the length of the tube? We don't have it. So let's say it's going to be unit length 1 meter, and this convection heat transfer coefficient is going to be, where is it? Do we have it? Oops. 100 watt per meter square Kelvin, and outer radius 0.078 meter. The length is going to be, we are going to assume it's going to be unit length 1 meter. So this is our system. To solve this problem, we need to determine the direction of heat transfer. What is the direction of heat transfer? From inside to the outside, or from the outside to the inside? Huh? So are we talking about heat transfer from inside to the outside, or heat transfer from the outside to inside? If you say the answer already, then how can I ask the questions? So when you want to determine the direction of heat transfer, the heat transfer is always from high temperature to low temperature. So in this case, the highest temperature is going to be the heater, which is 25, and we have two temperatures are lower than 25 degrees Celsius. Therefore, heat transfer direction is not from the inside to the outside or the outside to the inside. There are two different heat transfers. One is from the heater to the inner surface. The other one is from the heater to the outside. So there are two heat transfers. One is this way. I'm going to say Q1. The other one is this way. I'm going to say Q2. So you're right, from the heater. Then, if you want to determine, by the way, what we need to determine, I forgot that. We want to determine the heater power required. Okay. So if you want to determine the heater power, you need to calculate Q1 and Q2 and calculate the sum of Q1 and Q2. That is going to be the heater power required to maintain the temperatures. So let's calculate Q1 first. Q1 can be determined by delta T over R. What is delta T? 25, 6. 25 degrees Celsius minus 6 degrees Celsius. And how many resistances? Two of them. Conduction resistance and contact resistance. Conduction resistance, which is natural log 0.078 divided by 0.024 divided by 2 pi k 10 times the length of the pipe, 1 meter, plus 0.01, which is the contact resistance. What about Q2? The delta T is going to be between 25 and minus 10. 25 degrees Celsius minus 10 degrees Celsius. And how many resistances? Just one. Conduction resistance, 1 over H, 100 times 2 pi R 0.078 times 1. So that's how you determine the rate of heat transfer from the heater to each direction. And when you calculate Q1 is going to be 661 watt. Q2 is going to be 1715 watt. So the total heat transfer rate, Q, is going to be this one plus this one, 2,376 watts. So this is the heater power required to maintain, to have this system. What's going to happen if you provide less than this heater power? So the heater power is less than this one. What's going to happen? The temperature of the heater is going to decrease from 25. If you provide more heater power than this one, the temperature of the heater is going to increase from 25. That's what happens. To maintain the constant temperature, in other words, steady state heat transfer, you need to provide the exact amount. Any question about thermal resistor network? No? Nope. Okay, good. So that was the first part of this chapter 3. Steady state heat conduction without heat generation. Then now the second part is going to be steady state heat conduction with heat generation. But before we go in there, let's talk about one more thing, which is called critical thickness of insulation. Critical thickness of insulation. What is critical thickness of insulation? We don't know yet. That's what we want to study, right? So let's talk about this problem. So we have a pipe, water pipe, this much. And we have this pipe, and there's hot water. So the inner surface temperature is going to be almost 90 degrees Celsius. Outside is going to be freezing, minus 20 degrees Celsius. Not even Michigan. It's going to be somewhere Alaska or something. Is a typical temperature in Alaska? Anybody have been in Alaska? No one? I got a job interview there. Yeah, University of Alaska, Fairbanks or something. No, I didn't go there. I just got the interview request. No way. Yeah, Texas, Michigan is okay. It's actually better because I like the weather here. But Alaska is completely different story, right? It's another level, right? Anyway, so if we have this temperature difference, what do we expect? The heat loss in what direction? This way, Q. Then what kind of heat transfer is that? Conduction or convection? The answer is both of them, conduction and convection, right? So we have a conduction here and convection here. So what do you expect when you have a water pipe has a 90 degrees Celsius and outside temperature is minus 20? What do you expect? Oh, there will be a lot of heat loss, right? So what do you want to do as an engineer? Just leave it as is? You can do that. But you want to minimize the rate of heat transfer, right? Then what can you do to minimize the rate of heat transfer? Yeah, you can add an insulation. So I'm going to add an insulation about this much. So tell me one question. If you add an insulation, the rate of heat transfer decreases, right or wrong? How many of you think that that if you add an insulation, the rate of heat transfer decreases? Just two. And how many of you think that the rate of heat transfer increases when you add an insulation? None? What about the other 22? The answer is Yes and no. Yes and no. The answer is yes and no. Why is that? When you add the insulation, we add the insulation to decrease the rate of heat transfer. But the rate of heat transfer is not always go down. There is a threshold. When you add the insulation, what's going to happen? If you add the insulation about this much, why add the insulation decrease the rate of heat transfer? What about if you add the material that has extremely high thermal conductivity? Then adding that layer is going to increase the rate of heat transfer, right? So basically, you are going to add a layer whose thermal conductivity K is going to be very low, right? So if you add an insulation, you are going to create what? Another layer of conduction resistance that will decrease the rate of heat transfer. So when you add an insulation, that means in heat transfer, you are creating conduction resistance. Because of this conduction resistance, the rate of heat transfer goes down, right? Then, if you add this conduction resistance, is it just the increase the conduction resistance? Not necessarily. There's another side effect. What is the resistance outside? Resistance through this insulation can be determined by what? Natural log R2 over R1 over 2 pi KL, right? Then what about here outside? Is there nothing? There's a convection resistance. What is convection resistance? 1 over HA. A is going to be 2 pi R2 times L. So if you add the insulation, you will create this one. So that increases conduction resistance. However, if you add the insulation, this R2 goes up, right? Right? So if this R2 goes up, what is this whole thing? Convection resistance. If you add the insulation, you increase conduction resistance, but you decrease convection resistance. So you are trying to increase resistances so that the heat transfer goes down. But when you add insulation, yeah, you can increase conduction resistance, but there's a side effect. Convection resistance goes down because you are increasing the outer surface area. You are creating more surface for heat transfer. So what happens is that if you add the insulation, let's say that this is a heat transfer. This is the thickness of the insulation. If you add the insulation, we expect heat transfer goes down, but not necessarily. Heat transfer actually goes up. The thickness of the insulation is not thick enough to provide enough conduction resistance, but you are decreasing convection resistance. So, and then now insulation plays, so the conduction resistance dramatically increase. This is what happens. So when you add the insulation very thin, you are actually increasing the rate of heat transfer. So you need to add enough to decrease the rate of heat transfer. Then how thick it should be? There's one simple way to calculate how thick it should be. That is called critical thickness of insulation. That's what we are going to study this Thursday. Okay? That's all. Any question? No? And see you on Thursday. Yes. Oh, you want to take that? Here. This morning? Huh? Yeah, this morning, but I don't have any more. So this has this.